Okay, so hello everybody, thanks for coming. I'm going to talk about developing and optimizing code in the Wolfram Compiler. It's a kind of a follow-on a little bit from Tom's talk that he gave earlier. I'll try and go a little bit more in some lower level details and give you some examples of what we've been working on since the last release. So this is just an overview of what the Wolfram Compiler looks like. I'm going to be mainly focusing on this part, the code generation and the conversion to CPU instructions. So as you saw in Tom's talk, we convert Mathematica code to this Wolfram intermediary representation, Wolfram IR. And then that in turn is converted to the LLVM IR. And as Tom mentioned already, LLVM itself performs various optimizations. And you can target specific generated assembly code from that, or generate a library and get machine code that you can run from that. So in the type system in the compiler, there are, like as Tom I think already mentioned, a much wider set of machine number types available than there are in Mathematica itself. And it's actually much easier to develop things in this structured environment in the type system than it is to develop them in the kernel. We've also added support in this version for numeric arrays in the compiler. That's complete support for arithmetic and some structural operations. As Tom mentioned, we also have a number of new data structures and a number of new data types, strings and booleans, etc. In this talk, I'm going to be focusing on arithmetic. So initially, all of the arithmetic from both the compiler and the kernel were done through a library that we built up over time, or Wolfram RTL, the runtime library. And it lived solely in this library. As we extended this library and turned it into C++ and used template arithmetic so that we could support all the additional types like floats, 8-bit integers, etc. The new thing for version 12.2 is that all of the mathematical functionality, all of the scalar math functions in the compiler are implemented in the compiler itself. And that's a testimony to how fast the compiler is, or at least how fast the generated code is. As Tom mentioned already, there's still a problem with the actual speed of the compilation. The other thing is that it allows us to generate, to develop the compiler framework itself by implementing parts of the compiler in the compiler itself. We can generalize it and add features that are missing. And a third thing is that when you call a function from a library, it's essentially a black box and you know nothing about it. So you're just calling an external function with some parameters. Whereas the way that LLVM works, it can do a lot of optimizations when it knows more about the actual nitty-gritty of what goes on inside the function. So I'll give you some examples of that a little bit later. So as I said, it's a good test of the compiler infrastructure. We can then optimize the mapping to LLVM and specify a specific LLVM intrinsics from the compiler. And extend the compiler support by adding some sort of kind of C++ type templated features. So why is it good to use LLVM and what sorts of things can LLVM do? So in the old compiler, it essentially translates in a fairly dumb way. It's function by function exactly what your program is doing. And it does no kind of modern compiler kind of optimizations on that code. What LLVM can do is, once you have its intermediary representation, it can do all sorts of transformations to make the code more efficient. So it can do constant folding. It can look for patterns in code and try to optimize them. It can do common sub-expression elimination. It can do transformations of isomorphic forms, things like value numbering. It can switch loops. It can pull out invariant code from loops. So the sorts of patterns are, subtraction from 0, it's just a number. Subtraction from a number by itself with the proviso that it's not a floating point exception here. That's just 0, and twice a number by itself is just the number itself. So these might seem like trivial things, but they actually turn up quite commonly once you start to fold in and work on lots and lots of code. And another thing is value numbering. So that's kind of a generalization of a common sub-expression elimination. So here we've got a simple multiplication, an intermediary assignment, and another multiplication. But this assignment here is just resulting in the same multiplication as we had here, but because of the introduction of the intermediary variable, common sub-expression elimination can't work to reduce that, but the so-called value numbering optimization can work, and then this computation here is eliminated. It's just reusing this value. So these are sorts of things that LLVM can do automatically for us. That's one of the reasons why we want to use it. So you saw this in Tom's talk. I can thankfully skip through some of the details. I'm just defining a simple function in Mathematica, and this is just calling bit length. And all I do when I want to compile it is just add a type markup to say what kind of type number I'm interested in working with. So this is the definition of my function, and then I just call function compile on it, and it makes me a compile code function that works with integer 64 input and gives me a integer 64-bit output. So this is a machine integer on a 64-bit machine. Now, there's a lot of stuff going on here, and all you really see is the result of what's going on. So actually digging down inside helps to kind of optimize the code. So let's look a little bit. You saw an example of this in Tom's talk. So if I just take that bit length, simple bit length function, and I look at the Wolfram IR, then it's marked up as this, and these are kind of machine instructions that are going on. There's some strange stuff with bit XOR. There's one call to count leading zeros, and there's another one to count leading zeros. These are LLVM instructions. And then there's a subtraction. So I have the number of bits in my type, say 63 if it's a signed integer, and I subtract off the number of leading zeros, and that tells me how many bits I have. And then the bit XOR is something needed if I have negative numbers. Remember, I specified here that I'm working with signed integers. Well, signed integers could be positive or negative. So there's some extra stuff going on here that has to deal with when numbers are negative in order to get the right bit count. So the first thing when you're working on code is that I think Tom mentioned already that types, since the compiler works with types, it's a little bit different to working on Mathematica code. When Mathematica, you write a 1, there is only one machine integer, and so that's pretty unambiguous. But in the compiler, when you have 8-bit integers, signed and unsigned, 16-bit signed and unsigned, you need to be a little bit careful about how you write code. So in the compiler, when you type a 1 in your code, it's interpreted to have the default type of machine integer. And this is the default floating point type is a machine real. And the default complex type is a machine complex real. So if I write something like this in my function, okay, then this 1 is a machine integer 1. And I'm going to add a machine integer 1 to a floating point number and get a floating point number as a result. Because of the way that LLVM works, it's able to say, oh, okay, I know that this 1 is going to be added to a floating point number, and so it's going to automatically create a floating point number without casting it. So I don't pay any runtime penalty. LLVM is smart enough to optimize this and say, I know I'm going to be adding it to a floating point number. I'm going to make this essentially a 1 point here. But I need to be a little bit careful if I'm going to be adding an unsigned integer 8, because this is now a machine integer, 64-bit signed integer. I want to add it to an unsigned integer. The output for this is going to be a machine integer. So this is going to be up promoted to the machine integer type, which may not be what I want. So I need to be a little bit careful. So if I really want to be specific about it, I have to tell the compiler that this is, excuse me, it should be a 1 here, that this 1 that I'm introducing here really should be an unsigned 8 integer type. Okay, so that maintains the type information in this sum here, and I'm adding an unsigned integer 8 to an unsigned integer 8 and getting an unsigned integer 8 out. And we have some kind of simple helper functions that will just say, give me the number 1, which is the same type as x here, and that just avoids you having to retype the name of the type here. If I change this to unsigned integer 16, then this is going to be an unsigned integer 16 number. So it's good to write your code a little bit in this way rather than this way to avoid any kind of type ambiguity. Now, a numeric array arithmetic is fully supported in the compiler. At the moment, it still goes through the runtime library. So even though the scalar arithmetic is completely in the compiler now, the array arithmetic is still in Wolfram RTL. But it does work, and you can do all sorts of arithmetic now with different number types here. So here I've got adding 2 arrays or 2 vectors of integer 8 type, and I'm doing some computation on them, and this is the result. And I can mix and match them. So I have an integer 8 and I'm adding it to a float type. And it's smart enough to know about the coercion rules and things like that, and produces a result of the appropriate type. Now, of course, when I mix types in this way, I am going to do some type promotion or type coercion generally. So it's more efficient if you really work with arrays of the same type. You will avoid making a copy of something and having to cast it. So it's a good idea to work with numbers and arrays of the same type. And also, if you work on number theory type of computations, like I showed you with the bit length function, it's a good idea to work with unsigned integers rather than signed integers, because it kind of gets a little bit bit shifting of negative integers, etc. is a little bit undefined in C, and so we have to do some, 2's complement representation and that sort of thing. If we know that we're working with an unsigned integer, then that's just a native bit shift. It can compile down to a native bit shift and work more efficiently. So here's a little example here. So the first thing to do when you work on your code is to time it. So all this does is just makes a function called subtract and compiles that. And the second function here is going to call repeated timing, but it's going to call it inside the compiler. So repeated timing is a kernel function, and you can call it on any code. But repeated timing is also implemented natively in the compiler. And if you want to time in a fine-grained way your compiler code, it's a good idea to not call repeated timing outside of the function and get the function call overhead. It's a good idea to call it inside the function, and it really does measure the speed that your assembly code is executing. So here are 3 examples. This is calling the kernel function subtract here with the kernel function repeated timing. This is calling the compiled function subtract with the kernel function repeated timing. And this is doing the compiled function subtract with repeated timing inside the compiler. And you'll see that the time measurement here is quite a bit faster. It really is measuring the speed of executing subtract inside the compiler rather than the overhead of going through the evaluator and calling the kernel code. So this is really showing me the actual speed of subtraction in the compiler, rather than the function called overhead that's going through the kernel. And here's an example with GCD. So there are several layers to the way that we've built up arithmetic. So we've implemented something like 150 functions. The compiler now, the Wolfram compiler, now has more functionality than the old compiler with respect to arithmetic. And it's built up in layers. As Tom mentioned already, when you do arithmetic in Mathematica and when it overflows the arithmetic, it switches to big nums or it does other things. And the cost of checking whether an error goes on can be quite significant. And there's no way to switch that off in Mathematica. Whenever you type 1 + 1, it knows nothing about the fact that, that the number's not going to overflow. So it needs to use an integer addition that actually checks for overflow, which is slower than the integer addition that's available in a native CPU instruction. So we have, in the compiler, we have several ways of controlling these things. We can say, do I want to do checked arithmetic or unchecked arithmetic? And then we build up our functions using intermediary levels that can be used. And then we actually call native functions from LLVM or from the CMath library. I think Tom gave you an example of the CMath library in his talk. So let's take one example here. I'm going to call the function, the exponential function, a float version, not a double version. And then this is going to get compiled down. using the Wolfram compiler. And here I'm going to say, well, I'm going to natively call the C math library function from within the compiler. And let's just compare the two. So what happens when I call this, by default, the Wolfram compiler is going to call the native C math exponential function, but it's also going to add a test if overflows happened or not. So it's got some additional stuff going on here. And this shows the two things together. So this just shows that they give the same values. This shows that when I call the Wolfram compiler default exponential function, here it's checked for an overflow, it's issued a message and then switched to kernel arithmetic, whereas this one hasn't. It's just given me the IEEE infinity that comes out of here. So you need to be a little bit careful. If you switch off the error checking from the Wolfram compiler, you can get exceptions coming out of your code. So another bit about LLVM. So when you're writing your code, one thing that we found is we've tried to optimize code in different ways, and sometimes it makes no difference whatsoever. So here's one example from LLVM. You might think, oh, I'll try and optimize my code here. Here I'm just calling the native function and I'm multiplying something by 2, and LLVM is actually turning this into a left shift by 1. And all of these things are equivalent computations. So I do x plus x, or I shift x left by 1, or I multiply by 2, and they all compile down to the same thing. So if you think you're rewriting your code and optimizing it and you're not seeing much of a difference, you can dig down into the IR and actually have a look and see what instructions it's being converted to. So let's actually get to a couple of applications of the Wolfram compiler. What I'm going to do here is just write a very simple program that's going to compute a determinant here. I'm just going to multiply 2 of the values, multiply the other 2, and subtract them. The only trick here is that I'm going to do this in an unchecked block. So this multiplication and subtraction is really going to be using the native instructions for subtraction and compilation. And I'm going to write a little wrapper function here called test overflow test here. And I'm going to wrap that outside, and I can do this function now natively in the Wolfram compiler. And when I'm completely done, then I can go and see if it got an overflow or not. And that prevents the example that we had before with the exponential function leaking out into the kernel, these IEEE infinities or whatever. Okay, and now it turns out that this is not a very good way to compute the determinant. There is an alternative way, and this shows something new in the compiler. So an alternative method that's due to Kahan is actually to use a fused multiply add operation, or several of them, and it works like this. So you compute an initial product here, this initial product. This initial product then gets truncated to a floating point number. So it's 53-bit number by a 53-bit number. The product is 106 bits, and it gets truncated down to 53 bits. So there is an error here in this product. Okay. What I'm going to do is use the fuse multiply add. I'm going to feed it back these numbers that I started with, but with a negative value, and I'm going to add it to this truncated product that I have here. So essentially what this is going to do here is it's going to tell me which of the 53 bits were thrown away, and it's going to put that into a floating point number and store it as the error. Then I'm going to use another floating point fuse multiply add to add in the other bit of the determinant here to the bit that I've computed. I've computed this bit. I'm going to add in this product and subtract this away. I'm going to get a final result, and I'm going to add in the error from this product that I've computed with this fuse multiply add. So let's take a look at that here with this particular example. So I'm going to take these particular values for my matrix. I'm going to use a numerical approximation to pi and to e, and I'm going to use these rational numbers for my other entries. And these rational numbers actually come from the continued fraction approximation to pi and e, so you can see where they come from here. This is an approximation that's close to pi, and this is an approximation that's close to e. Now, if I use my naive determinant computation, this is the result that I get here. And if I use this extended fused multiply method that feeds back the error, then I get this result here. And you can see that the two results are the same for the first 8 digits, and they differ in the last 8 digits. So what I can do is, in Mathematic, I can analyze this, obviously, using arbitrary precision arithmetic. So that's what I'm going to do here. We don't have fused multiply add arithmetic, so I'm just going to use the naive method, but with higher precision, 32 bits of precision. And this is the result that I get. And you can see that the fused multiply add method has got a completely accurate result through all the bits, whereas about half of the digits of the naive method were incorrect. And the error in this method, fused multiply method, has actually been proved to be correct too. In the worst case, 3/2 alps. So the last thing for this example is to say, well, how did that compare performance-wise? I'm doing this extra work. I'm using these fused multiply add operations. I'm doing an extra product. Let's see kind of a performance profile of the compiler of these things implemented in the compiler. So these are my methods. This is the naive method implemented completely in unchecked arithmetic. Okay, so I'm just switching off any kind of overflow checking. And this is the fused multiply method, and you see that they really are very close in speed. So this extra product that I was computing was not really affecting performance very much at all. And this is the code that I showed you, where I had an additional wrapper function that did an overflow test right at the very end that didn't interfere with the intermediary computations of the determinant, but it just did a final floating point overflow test. And that doesn't affect the performance very much at all. What is not so good is the way that Mathematica does it. It does a floating point multiply and then a floating point error test. It does another floating point multiply, another floating point error test. Then it does a subtraction and it does another floating point error test. And all of these can cause CPU resource exhaustion and also branch prediction problems. And you see that even when this is implemented inside the compiler that generates very efficient code, it's quite a bit slower to fully check every floating point arithmetic operation for a floating point error. So we get something like a factor of 4 here. So that's one performance tip. That is to do a lot of your arithmetic by switching off the overflow checking and write some kind of higher level function that's going to go and analyze the result and check it. So the next example that I'm going to show you is a comparison of integer arithmetic, the greatest common divider. So the most commonly known method to compute the greatest common divisor is due to Euclid. So essentially you take two numbers and you find the remainder of division. And you take the smaller of the two input numbers and you use that. And you take the remainder of the division of the two numbers and you use that. And you continually compute the GCD in a recursive way. There's another algorithm that uses only binary operations. So the problem here is that this is essentially doing integer division, which can be quite expensive. There's another algorithm first published in the late 60s that essentially does only subtractions and bit shifting. So it tries to reduce everything to odd numbers, then subtracting odd numbers gives an even number. Then it will shift out the zeros in that even number, get another odd number, and then continue that kind of evaluation. Now, STD GCD, which is what we had in some earlier versions of Mathematica, because the Wolfram RTL was written in C++, uses a version of the Euclid GCD. What I'm going to show you here is that the compiler implementation of this is just as fast as the C++ code was from STD GCD. And I'm going to show you that the compiler implementation of this is even faster. And I'll try to explain a little bit why that's the case. So three things I'm going to do. I'm going to use a loop instead of recursion. I'm going to use unchecked arithmetic. Now this is unchecked integer arithmetic, not floating point arithmetic. That means that I don't check that integers wrap around, because I know that every step in the GCD is a reduction of integers. There's never going to be a case where I subtract two things and I get something larger, or shift something down and get something larger. And the other thing that I'm going to do is a bit like Tom showed by disabling interrupts in function compile. I'm going to use a lower level primitive to disable it locally in this function. So here's my GCD function for Euclid. It just says swap the two if one is greater than the other, and it just does a while loop testing when something becomes 0 and just returns the value. And this is the remainder step, and then this is swapping the smaller value to the first value and taking the remainder, which is always smaller, as the second value, and it just loops around here. Okay, so this is really Mathematica code with a little bit of compiler syntax and some markup for efficiency, and then the type markup that we have. Let's skip this thing. Let's go to the binary GCD code. Okay, so this is my code for binary GCD. It's a little bit more complicated. You can essentially ignore this stuff. It's pre-processing by removing common powers of 2. The essentially important stuff is down here. What I'm doing is, while the numbers are different, I'm going to see which one of the two is greater, subtract it from the other one. Then I'm going to call this LLVM specific function that's going to remove or tell me how many trailing zeros does this number have. I know at this step that it must be even because I'm subtracting two odd numbers. So I'm going to say, well, you know, how much is it even? How many zeros does it have? Is it 4? Is it, 8 or whatever? And then what I'm going to do is take that number of zeros and shift them out of the number and create a new number. That's odd again, and just continue around this loop until I'm done. Okay. Now, generally, this is doing a lot more cycles than the Euclidean algorithm. But here's a comparison of the two implementations. So this is the binary method. This is the Euclidean method. And here's another one that we just implemented for completeness that interleaves the Euclid step and the binary step. This is a particular set of inputs that gives the worst case for the Euclid's algorithm. What happens here is that every single division is going to have a quotient of 1. So it's the slowest convergent pair of values for the Euclid algorithm. So this is the worst case, in a sense, the worst case timing of the Euclidean GCD method. And you see that the binary GCD method is more than an order of magnitude faster. And on the other hand, this is the worst pair of values for the binary method, because what happens here is every time I subtract numbers, I make an even number, but that's only got 1 0 bit in it. So I'm only knocking off 1 bit at a time as I go through that algorithm. And here you can see that the binary method is actually slightly slower than the Euclidean method. And then if I take random inputs, randomly generated inputs, and these are according to the distribution theory of random numbers. This is what I would expect in the Euclidean algorithm. These would be the quotients that I would expect. I'd expect a quotient of 1 40% of the time, quotient of 2 17% of the time, and these random numbers were generated from this distribution. Then again, I see that on the average case, these random average generated numbers, that the binary method is quite a bit faster than the Euclid method, like a factor of 6. And the other important thing is that the binary method is really quite robust. I mean, you throw any pair of numbers at it with good or bad properties, and it has a pretty good, nice stable timing. So the other thing that we saw here is that when we implemented this in the runtime library in C++, and we implemented it in the compiler, exactly the same algorithm with exactly the same primitives, we saw that the compiler was actually generating faster code, like 30% faster code, and we couldn't quite figure out why for a little bit of time. And the reason for that is that, as Tom said, when you call function compile, it works in memory and it's able to use CPU instructions that are native to your processor. But when you build a library, especially Wolfram RTL and Mathematica, they're built for a generic x86 processor, and they can't use optimized instructions from more modern processors like Haswell or whatever. And so this just shows that. This shows that if I take a function compile of my GCD function, and then here I export it and load it back in as a library. So this is actually making a physical file that's using different optimization settings to function compile. Then I can see that it is about 30% slower. This is making a generic library that I can share with other people, to be fair. Now I could of course make a library that's specific to my platform, and I could bring this down. But then if somebody's got like an older CPU, I wouldn't be able to share that with them. So that would be a problem. And this is the last thing. Now, I'm not expecting users to go down to this level necessarily, but just to show you that it's the sort of thing that you can do if you want to. And that is to actually go and use tools. You can take code from the Wolfram compiler and you can put it into some third-party tools. Let me just show you. So this is one example here. Where we've taken code generated, this is our GCD code generated from the Wolfram compiler, the LLVM code that's been generated. I just paste it into this compiler explorer and it will generate for me, according to what CPU parameters I've put in, it will generate for me the machine code. And what I can see here is this, this particular instruction is the one that I'm interested in because of the parameters that I've used here. I said use all of the modern CPU architecture optimizations. And I see this TZCNT instruction here that corresponds to my LLVM count trailing zeros function in my binary code. And that's a specific instruction that's available only in Intel Haswell and later processors. Okay, so I can use the compiler and I can generate, you know, highly specific targeted machine code. And the last thing that I can do, if I do, like I said, if I generate two versions of code and I want to compare them, I can not just time them, but I can actually put them into something like this third-party thing here. Here on the left is my determinant code, the naive one, which just does, you know, the product, and the subtraction. Here is the assembler code that's been generated. And here is an actual performance profile that comes from this LLVM MCA machine code analyzer. And it tells me if I do 100 iterations of this code, this is how many CPU instructions I'm using. This is the total number of cycles, CPU cycles that I've made. And then there's a whole bunch of stuff about latency and all sorts of stuff in the processor that's telling me, you know, how these registers are being used and what kind of the delays of the operations are. And a similar thing here. Here's the code generated from the Wolfram compiler, the LLVM code, that's using the fuse multiply add method. And here's the same thing here for this fuse multiply add. And what you can notice is, if you remember, the timings were very similar when I switched off the checked arithmetic. It's a fraction of 1.08 seconds, 1.13 seconds, something like that. And you can actually see why here, that this fuse multiply add, even though it's doing an extra multiplication, some of the register usage and stuff is more optimized. And so it's only using 1200 CPU instructions, whereas this is using 1100. And that's only a difference of like, less than 10% or something like that. So it kind of bears out the timings that we got when we used repeated timing to test them. So that's the last thing I wanted to mention. So in conclusion, all of the native mathematical arithmetic is now built into the Wolfram compiler. It's something like 150 functions. It was a lot of meticulous work to build it all in there, but it's definitely worth it. LLVM can do a good job of optimizing that. We can generate much faster code. We don't need to call external libraries to do arithmetic now. There's no function calls. Also, LLVM can do a lot more optimizations on the code and analyze the code a lot better and produce much better machine code as a result. There's no more guesswork for code optimization. If the compiler was calling Wolfram RTL, essentially that's a black box to the user. and the user has no idea what algorithm that's using, and we have nothing to hide about the implementation. We're very proud of it. So now all of the code for the arithmetic is written in Mathematica itself. You saw it slightly stylized Mathematica, but you can use that as a starting point for your code, or you can take bits and pieces of it with ideas of things that you want for your own functions, and you can use those in your own code, or you can use intermediary utility functions and call them in your own code. So it's a completely open and transparent workflow. The idea is to start with the Wolfram language code, mark it up with a type, then use some kind of stylized extensions, maybe think about aborts or checked or unchecked arithmetic. You can use the existing code base as a starting point. So that's the state of this version. For the next version, we'll be working on array operations and building those in natively. So they still call a lot of the numeric array operations for arithmetic still call the Wolfram RTL. So the next version will be working on moving those all natively into the compiler, and then linear algebra and lots more. It never stops. So okay, that's everything. So I hope that was overly long. Thank you. Oh yeah, if anyone's still listening. So we do have a question and answer session in about half an hour, I believe, with Tom Wickham-Jones on the compiler. So if there are any questions that anyone has, we're happy to answer them. Thanks again.